So, welcome to this session entitled, Don't Bite Off More Than You Can Chew, Take It in Chunks. Well, there might have been a time way back then, many years ago, you were a junior school programmer, you talked to a senior colleague and said, I have this table, I need to loop over that. How do I do that in SQL? And that senior colleague just smiled at you and said, no. In SQL, you don't write loops. You write set-based statements. You work with all data at once. And as you progressed with your career in SQL, you came to master those set-based statements. You come to love them. They became your way of life. But then every once in a while, you might have encountered this really large table and thought, should I really take all at once? Or maybe you could, but maybe you should take it in chunks. So my name is Erland Sommarskog. I live in Stockholm, where I work as an independent consultant, and I've been an MVP for many years. The way to get in touch with me is my old-fashioned email, sql@sommarskog.se. And I maintain a website, sommarskog.se, which you can see as well a small collection of large articles that goes in depth in a couple of topics. However, this is only a session I haven't written about this topic. And you find slides and scripts for this session is available on my website, sommarskog.se/present, and you will also see that my contact information at the end. So this is my agenda. I will start with talk about two scenarios where chunking comes into play. Here with some kind of cryptic subtitles, don't bite off more than you can chew and be nice to others. Then I will talk about how to implement chunking, performance and other pitfalls you can run into, and that will be the main meat of the session. And I will close with talking to the third scenario when chunking comes into play, but for error handling, here with the cryptic subtitle, when all or nothing is not what you want. So say this. You have a table and you want to perform some operation on the entire table, or at least the better part of it. So for instance, you find that this table, there is an int column, which is the key column. When you look at it, wait a minute, the max value starts with 2. What? That's 10 digits. Wait, it's going to explode very soon. We need to change this to bigint. And of course, you could do that with all the table. But then you may say, nah, I'd rather create a new version of the table and copy data over with insert for one reason or another. Or it might be that you have added one or more new columns to a table, and then you want to initialize them, maybe taking values from other tables and so on. You want to do this for all rows. Or it could be a purge operation. Now, if you want to delete all rows, that is truncate table. But let's say you want to get rid of 50% or 90% of the rows. And this table is now 300 gigabytes in size. Now, what if you try to do that operation as one single operation? What could happen? Well, it could be a lucky day and things may go just fine. However, very much likely though, the log file would start, the transaction will start to grow violently. And there will be lots of alarms that goes off and people will go crazy. Or it could be temp to be, both the data or the log file, but also go out of bounds. Maybe the operation is a little more complex than I suggested on the previous slide. So you fill up temp tables, there are spool operators, etc., etc., etc. But it's also maybe a possible issue with a buffer cache. If you're only going to do a plain one single scan, you're going to read data into the cache, do some work on it, and it will fall out of the cache directly. But let's say you need to come back to the same place many times, and then you will have to read it from disk every time. So that could also be bad. And also what about if you have to cancel the operation for some reason? That rollback could take a very long time because that's such a large operation. Now, the remedy to all of these is to split up the work in chunks. Rather than working with all at once, no, you don't take one row at a time, but you take reasonable sized chunks at a time. And of course, that chunk size should be small enough so you avoid filling up the transaction log and the log temp to be. So any operation on any chunk should fit within the temp to be a lock. But at the same time, don't make the chunks too small because the chunking will head over it because you are doing a loop, and so bigger chunks will be more efficient. Now, the obvious question then is, what is the right size of my chunks then? How many rows should it be? And hey, you know the answer. It depends. And it depends on a whole bunch of things. I mean, first of all, what is the current size of your log file in temp to be? Let's say that both of them are already 10 terabytes. Well, then maybe you can work with that 300 gigabyte table in one go. But you also don't only look at the number of rows. Let's say this, there is only 1 million rows in that table, but there is a lob column in that table that you need to work on. And the average size of that lob column is 1 megabyte. You're looking at a 1 terabyte table. Probably do some chunking here with, of course, fairly small number of rows in the chunks. But all this said, I do have kind of a standard value that I tend to use for these kind of operations. That's 5 million rows. And this is not completely taken out of thin air. A couple of years back, I was working, I had a table with 40, 50 columns, no lob columns, but it was fairly wide. And I think at least 200 million rows at some sites. So I wanted to see so I wanted to do this in chunks, but I want to find out what is the best chunk size. And I found that when going from 500,000 rows to 5 million rows, I still gained performance by, well, 10, 15%. I did actually stop at 5 million rows. But as they say, your mileage may vary, and you will have to try this out for your table. Now, keep in mind about the transactional. Even if you're doing chunking, you could still explode the log all depending on how often you are, because no matter, you are working with a lot of data, you will produce a lot of transaction log. So, of course, the simple way out is to put the database in a simple recovery, but I don't like doing that in production because it breaks the log chain. And of course, if you are an AG, you can't even do that. Don't even think of it. So with full recovery, you may have to increase the backup frequency, maybe to do it as often as every 1 minute and change the schedule. Because if you only do, like say, every 15 or 30 minutes, the log could still explode at that time. You could say, well, couldn't I add a backup log to my chunking script? Yeah, you could, but then only if you write to the same place at the same name convention as a scheduled log backup. Because keep in mind, it could be that 2 days later you find that, oh, wait a minute, we have corruption. And oh, it has been in the database for a week now. So we need to restore an old backup and apply logs. Yeah, and that's also why you don't want to go into simple recovery, because you will break the log chain and will lose that option. Now, being nice to others, this is a different scenario from the previous one. For the previous one, it was like a really big operation, like you would do in a maintenance window. You have the server and the database to yourself. This is maybe a smaller operation, maybe only 5 million rows in total. But now you have to do this in a live system because it's part of the application. Now, if you try to work on all these 5 million rows at a time, you could take up too much resources in terms of CPU and memory, etc. And even more important, you can cause blocking or deadlocks. So this case, again, you would split up the operation in chunks, now with a fairly small chunk size. But the operation will be less efficient as such, but the overall system health will be better. And in this case, that is kind of a number you want to look for the chunk size, and that is 5,000, which has to do with lock escalation. Let's say you're going to do a purge operation on the left side of the table, somewhere over there. And the users are mainly working on the right side of the table, on the current data. So you want to avoid conflict with us. So you don't want to do a lock escalation and lock the entire table. And if a query takes more than 5,000 lock approximately, SQL Server may then escalate to table level. So in this case, you could actually run a test operation with different chunk size to see if you get any locks, table escalation or not. So let's do this. I've got a database, big DB, which is today's demo database. We're going to do a few more things in this one. And I'm going to start the transaction. And what I'm going to do there is I'm going to delete 2,500 rows in this table called big trans. I will come back to this table later on. And what I'm going to look at is a couple of columns in SysDM translocks. So I will look at the resource type. That is, what kind of thing am I looking? How am I locking it? And what is the ID for what I'm locking? Resource associated NT-ID, which could be a table. So then I'm going to try to get the table in. And how many of these do I have? And then you're just going to roll this back. So let's run this and yeah, that is what happens. Sorry, folks. I had some issues before starting up this session because normally I do this on my laptop and I have not loaded this database. Let's see if I can do this. I'm not sure even if I have it on this disk. I might even have the space for it. Let's see. Oh, no, I will have to, sorry, folks. I will have to just tell you what will happen. I don't have this database on this VM. I'm very sorry. So what happens the first time is that I get a total 5,000 locks on the 2 indexes in this table. And thankfully, let's see, I will need this one. Oh, okay. We take that when we arrive there. Well, sorry, folks, this demo will not work out. This session will not work as really as intended. There will be some issues at the end as well. So anyway, when I run this normally, I get 2,500 locks in each indexes of the table. So that's exactly 2,000. But those are key locks. And there are also intent locks on page and table level, but you should not care about the intent locks they call IX. In fact, then I change this to 3,000 and I only get one big fat table lock on the table. So that's too much. So the whole idea is 5,000 locks includes, so if there are more than one index, you have to account for those as well. Okay, so when you do this, you should see X locks on key and read resources. Key, that's a lock, row lock in an index, and read, that is when you have a heap. If you see X locks on an object on page level, that means that your chunk size is too big. As a matter of fact, X locks problem, if you see object, that probably means that you escalate at the table level. If you see page lock, there's probably something with your indexing, because you will never escalate to page level. Those are taken from the beginning. But you might see IX lock, so-called intent locks. They will be an object of page, because they are just saying, hey, I'm doing work out down somewhere. So they're just placeholders for the work that's going down further down there. Okay, so let's now talk about the challenges with doing chunking. So it's not that chunking is a really wide adventure, like going out like a multi-day hike, and you need lots of equipment, tents and emergency, maybe a satellite telephone. No, but it's not really a walk in the park either. It's more like, well, doing let's say a forest walk. You need some sturdy shoes, because you might have to negotiate a stream or two. You could, well, slip on a stone or trip on a branch. So those things could happen. You have to be a little bit careful. First of all, you need to write more code. This means that there's more code that can have bugs, and there is more code to test. It's just no way around that. You also have to think about, how is the application affected? And I will come back to later on what I really mean by this, but the application could be affected by you doing chunking. And what if the work is interrupted halfway through? How to deal with this? And most of all, performance. Because if you do it the wrong way, the chunking could be worse than doing no chunking at all. You have to be careful. And we're going to start, I'm going to take these points more or less from the bottom and up. So is this a good chunking operation or not? This is the first chunking operation we're going to look at. So what I'm doing here is that I've added a new column to my some big table. And I'm saying, OK, I want a chunk size of 5 million rows. And I'm going to loop as long as my row count is equal to the chunk size. So I say, just update top chunk size and new column, put some value, new column is null. And then I capture the row count. So the last chunk would be probably less than the chunk size, so then I know it's the last chunk. Now is the question, is this a good operation or not? Think for this for a second while I get some water. No, this is not a good chunking operation. The reason for this is that the first time it goes quite fine. Let's go server rows, the chunks of okay, I have 5 million rows, I can update these. The next time it has to just go way through these 5 million rows that are already updated to find 5 million rows when new column is null. And then next time 10 million rows, etc., etc. Let's say that this table in total size is 500 million rows. So doing this loop is equal to doing 50 table scans on that table in average, because the last scan will be the full table. So that will not be efficient. So when you're doing chunking, indexing is critical. You must always define your chunks to work over an index column, because else you're going to scan that big table again and again and again, and it's going to be worse than if you did not do chunking at all, because it's going to take such a long time. And also I would say this, the larger the chunk size, the more imperative it is to use the clustered index. Because let's say well, there is an unclustered index I can use for this, and this server looks at this, wait a minute, 5 million kilocubs? I'm going to do that. No, I'm going to scan that table. So for smaller chunk sizes, well, an unclustered index may work, but then again, 5 million rows, still 5 million kilocubs, which is a bit expensive. However, sometimes there might be business logic that may constrain you, or you might be joined into other table, which may call for a different strategy. And I will briefly touch the last thing and give an example of that later on. Now, this table, Big Trans, this is something I got from a blog post by Adam Mechanic, Big Adventure Works. And this, well, to be a demo table, it's quite big. It has 31 million rows, 2.2 gigabytes in size. But well, for like a real world table, it's still a small table, I would say. So anyway, it has 5 columns, and there's also non-transaction ID, product ID, transaction date, quantity, and amount, and there's a non-clustered index, which, as you might notice, is, as a matter of fact, it's a second clustered index, more or less. And anyway, there are some data types. I think, oh, my business is going to grow, so I'm going to have big int here. Then these, why is this date time? I want this date quantity int. Oh, I don't need that. I could small it, but number, that's a funny data type. And of course, I don't think these should be nullable, because what that makes sense with the transaction without the date, or without the quantity, or without an amount. That's weird. So anyway, I want to do these changes. And of course, I could do that with all the table. And when I tried this on my laptop, I found, well, first of all, I need to drop the primary key and the non-clustered index and recreate them at the end. Then I need to run for all the table, all the column statements. And all of these will rebuild the table because they're all size of data operations because of the type of changes. So when I ran this on my laptop, it took 984 seconds and the transaction log grew by 20 gigabytes and the starting point was 700 megabytes. So what I did then, was I created a table called new trans with a clustered index in place, but without the foreign key and the non-clustered index, because I found out loading the data that way is faster. And then I copied all the rows in a single insert statement. Now, then I created the foreign key and non-clustered index, and the total time for this operation was 6 to 8 seconds, and the transaction log grew by 7 gigabytes. Now, let's see if we can improve this by doing chunking. So here is a generic way to write chunks. So the first part of this is really not what you need. So this is just a procedure, and I have the chunk size as a parameter. And the reason for this is I made lots of tests for this session to do this, and it was practical for me to have a procedure and have the chunk size to do a parameter. But for a thing like this, like just rebuilding a table, which is a one-off, you would use just a procedure, and you would probably hard code the chunk size. That would be all right. But the rest of it is kind of the pattern for driving chunks. So I get a min ID and a max ID, and those are my chunk boundaries. And I start with finding the boundary for the first chunk, which is simply the smallest transaction ID in big trans. Then I will keep on looping as this one is not null. Then I have this subquery here. Select top chunk size transaction ID from big trans, where transaction ID is greater than my lower boundary, ordered by transaction ID ascending. And I get the max out of that, and that gives me the upper boundary for my chunk. Now, then I'm going to do insert, new trans, select data from big trans, where transaction ID between these two chunks. And then the last thing I do with the loop is I got to find the next upper boundary by saying select min ID, select min ID like min transaction ID, where transaction ID is bigger than the upper boundary. And I will keep on looping. At the end of the loop, I will recreate the non-clustered index and the foreign key. Now, I like to dwell on this pattern a little bit because what is interesting here is that this one is suitable for any kind of table. Well, not any kind of table, but for anything, for any single column index you may have. This could be an int. So in this case, I have int. You might say, couldn't I just do max ID equals chunk size, min ID plus chunk size minus 1 or something like that? Yeah, but let's say if there are big gaps in the IDs, then it might, all of a sudden you might have a chunk with 3 rows. This makes sure that you have the full size of all chunks. And furthermore, this pattern will work with dates. It will work with strings. It will work with anything you can put an index on which you can have as a primary key or clustered index. It will even work with multi-column keys to some extent, and I will come back to that one later on. So how does this work out there? Well, so I like to remind you these types include storing the foreign key and the non-clustered index because I wanted to compare with a kind of real world operation. And what you can see here is if the smaller chunk sizes really comes with a penalty. It's really quite about slower when doing this. We can also see here, as long as I keep the chunk size below 1 million, well, the transaction log doesn't grow except for the smallest chunk size for some reason. And okay, this doesn't stand out very clearly, but this is kind of a sweet spot, 1 million rows, probably because we're having the biggest chunk size where the transaction log doesn't grow. But keep in mind, this table is only 2 gigabytes, and in a real world scenario, you wouldn't even dream of doing chunking in this one. And also, I should say that data is from my laptop, and if you're going to try this I'm going to give you the link to BigDB at the end. Testing may yield different results. Now, there are some things here to think about when it comes to optimization, because these min ID and max ID, they are variables, and therefore the optimizer has no idea about the hit rate. We're going to make a blind assumption and say 9%. Something like that. Now, if you're then joined into other table, because some of these kind of operations are a little more complex than the one I've shown you, well, that of course, that could affect the query plan. And I ran into this issue a couple of years back. I was working with a table and I needed to add some more columns to it. And I developed a chunking script. I actually have a tool to do this. But in my test database, I had 30,000 rows in the table, so there were no issues. But when my customer eventually took it to their customers, well, at one side it took, I think, 12 hours, and on the other side they gave up after 24 hours. And when I heard about this, I said, oh, what am I going to do about this? I don't need to do it because I wasn't actually working with that customer very much anymore. But another guy at that site was very smart. He said, try option recompile. Oh, that was it. Now it took 20 minutes to do that load, where it previously had taken 24 minutes. Sorry, 24 hours. Because now with option recompile, the optimizer realized, okay, oh yeah, we're going to hit this many rows because I got these values here. Okay, that's going to be great. I'm going to use this plan, and it was ran very well. Now, for big chunks sizes, that should not be a problem because let's say one chunk let's take, well, I don't know, 1 minute to process, and it takes 100 milliseconds to compile. That is not an issue. But if you have, let's say, small chunk sizes, and let's say it takes 100 milliseconds to compile, 100 milliseconds to process, then you have a considerable overhead. That is not going to work out. Well, there is another option. You can make the chunk boundaries into parameters by pushing them into an inner scope, like an inner stop procedure. Well, an inner stop procedure may seem like a bit of extra work, but well, you can also do this. Simply use dynamic SQL. Well, this is not very dynamic. It's very static, but you are passing these as variables, so the optimizer can sniff the values for the first batch and then reuse the plan. And hopefully, this may be a good plan that is good for all chunks. Now you might say to yourself, yeah, but for this plain case, nothing can go wrong here. It's a trivial plan. It's going to use, oops, sorry about that, folks. It's going to use the clustered index. Well, yeah, I thought so too. But look here at these numbers. I got a drastic improvement with dynamic SQL. From 299, I slashed the performance with a factor of 3 for the smallest chunk size. And even when I used option recompile for the smallest chunk size, it was an improvement. Although for 5,000 rows, the overhead killed me for the recompile. And then there is a bit of a problem here. This here is not compilation overhead, which you see here, the 78, 76, and these values here. The reason is actually there's a small difference in the plan. With optimization with apparently backfires, so it takes longer time. Now, I need to point out one thing here. This was the data when I got for the first time when I wrote this session in early 2019, working at SQL 2016, the build that was current at the time. Then I reran these tests like one in here 1.5 years later on because I was doing this session in past and wanted to have to have fresh data. And then both on 2019 and the then current build of 2016, the numbers were not equally drastic. I think I got here was like 145 seconds rather than 299. But I kept these numbers because they're kind of more starting. But still, yes, you get an improvement by using sniffing, even maybe for the simple cases. Now, we're going to look at a different operation here because it adds some more interesting things when I tried this one. So in this case, I got a table here called big orders. I don't know if my mouse is actually displaying on the sharing. Can anyone tell me? Do you see the mouse pointer? Oh yeah, you might do. I'm not sure. Oh, let's see here. Oops. Well, sorry. Okay. Because I might occasionally drop out of the on my outside screen, and then I don't know if, of course, you're not seeing that. I'm sorry about this. So anyway, so I got this table called big orders, which has 5.1 million rows, and it's 1 gigabyte in size, and I joined into this big details table, which has 50 million rows and it's 3.8 gigabytes in size. And what I'm doing here is I'm going to add a column called total amount. Whether that is a good idea or not, well, it's not part of this session. Anyway, I'm going to add a total amount where I need, of course, the total amount of the detail of the products, and also going to add the freight. Now, when I tried this one, I was in for a surprise because for the lower chunk sizes, dynamic SQL was slower. That was not what I expected. What was going on here? I was scratching my head, but I did find the reason. The reason it was this. The big orders turned out to have sample statistics, and the lowest ID in the history was 13,063. So when I did this for a chunk size of 1,000 or 5,000, the first chunk was entirely outside the histogram, and the SQL Server assumed, well, maybe one row, maybe a little smarter now with the new cardinality estimator, but still way too low, and therefore the plan was not the best one. But once I've moved up to 25,000 rows, well, it was a different matter because now the first chunk was inside the histogram, if only partially, but it was good enough to get a good plan. Now, so what can you deal with this? Well, you can, of course, do update statistics with a full scan to make sure that you capture all the smallest values. But it's important when you do this that you only do it on the index that you use for the chunking. Because if you only say up to statistics big orders with full scan, it's going to do it for all columns and that's a full table scan for all non-index columns. That's going to take a long time. And the times you see here includes doing this operation. So, but although your situation, you might turn out that doing this up to statistics with full scan may take too long time. So you might have to think of a different strategy, like, for example, starting in the middle so you get the first chunks get better. Now, one more thing I like to discuss here. So why do we use dynamic scale and recompile? What is really the key here? So here is the same operation, but I've twisted big orders. So the clustered index is now on custom ID, and the primary key order ID is non-clustered. But it's the same, and I'm doing this both chunking over custom ID and over order ID. And that also, let's now imagine that it's not 1 million rows, but let's say we have everything here is like these are not 1,000 rows, like it's like 1 million rows, which we think is a reasonable chunk size. And this is not seconds, this is minutes. It's just let's just imagine. So that's 3 days. So that's why we're going to use dynamic scale and recompile. Dynamic scale option recompile. We're going to avoid the complete disasters where things just goes on forever. And also, interesting observation here, it's kind of in passing, but if I do the chunking over the non-clustered index, I actually get better performance than doing over the clustered index, because now I'm aligned better with the other tables that I'm joining to. So that's an example of which is not always best to loop over the clustered index. You have to look at the entire query if you're doing something more complex. Now let's discuss a multi-column key. So let's say this B details table. It has, sorry, I was going to check on time. Well, that seems to be good. So this B details table, it has a primary key on order ID and product ID. And there is up to 600 products per order. Well, could we just ignore the product ID and do the top loop over order ID and ignore the product ID? And of course, if you're going to do 5 million rows at the time, well, some chunks may have 5,600 rows. Who cares? Not a big deal. And believe me, you want to stick to this pattern as long as you can, because the alternatives, as we'll see, are not really palatable. Now, but it could be the case that there could be like 10,000 products per order. You must not exceed a chunk size of 1,000. And keep in mind here, when I'm saying 10,000 products per order, just imagine any multi-column key and, well, all the kind of distribution it might be. And this is just one example. So in this case, we need to find something else. We can't just ignore, we have to look at the products as well. Well, then you might say, well, just extend that top logic to just both keys or more keys. How difficult can it be? Well, yeah. So I'm going to warn you, this demo, or it's actually not, I'm not going to run any code. So it doesn't matter that I don't have the database, thankfully. I'm just going to show you some code. But this might go on a little bit too fast for you, but it's for some of you, but there is actually kind of point with it. So anyway, this is update price simple, and this is the same logic we had before. So I'm taking the chunk size as parameter. I got my min ID, my max ID. I've set min ID to the smallest order ID in big details. Keep on looping as long as that one is not null. I do this subquery, select top chunk size, where the order ID is greater than min ID, and max ID, get the max ID out of that. So I get the upper boundary for my chunk. Then I do my operation, and this is a really silly one. I'm just multiplying the price with 1.2 because I did this only I wanted testing chunking operations. So I didn't care for anything that was really meaningful. And then here I get the smallest ID for the next chunk with order ID is greater than max ID. And for the case with, well, 5 million rows and 600 products per order, no issue. But now, as we had said, there could be 10,000 products, and I must stay below 1,000 for my chunking operation. I need something else. So here's update price double when I do this. Again, the chunk size is a parameter. I got quite a few more parameters here, and I got a min product order ID and min product ID to define my lower boundary, my max order ID and max product ID to define my upper boundary of the chunk. And I also need a stop order ID, stop product ID in a game over variable. And I'm starting with getting the endpoint. And I can no longer use min because I want to find the smallest order ID and the smallest product on that order. So I need to do a top one order was ascending, the order ID ascending, product ID ascending. And then I also want to find the last order and the last product on that order. And I will keep on looping as long as game over is not 0. I need to initialize this max order ID and product ID to null for reasons that will prevail in a second. Then I'm doing again this select top chunk size. But now it's a little more complicated because I have to look, well, the order ID is equal to my lower boundary, and the product ID is greater or equal to my lower boundary, or order ID is greater than my order boundary. And I say select top chunk size. So this will give me all the orders and products for my next chunk. And then I capture, then I do row number, and I capture this one with say max order ID is equal order ID, max product ID equal product ID for a row now equal chunk size. So that is the last one in the chunk. Now, for the last chunk, I will typically not have chunk size rows. So this select will not qualify anything at all. And when you do variable assignments in the select that doesn't qualify anything, that does not set the variables to null. It just leaves them unchanged. And that's why I need to set them to null up here. So anyway, I'm going to check, did I get a row? Yes. No, sorry, in this case, did I not get a row? I do have null. Okay, it's game over. And I'm going to set the upper boundary to my stop variables that I had. Now, then I'm going to do this, and there are quite a few cases to consider here. First of all, did I move to a new order, or did I stay within the same order? So this is the situation. Yes, I moved to a new order. I have to take all the remaining products of that order, and for the last order, I take the first couple of products of that order, and take all orders in between. Do you like that or condition? It looks a bit nasty. And as you can see, I have option recompile here. And here, well, this is all in the same order, all the products on that order. And eventually now, if game over is equal to 0, this means I'm going to find the next chunk, which is again a select top one query, where again with this a little more complicated condition. Now, when I tested this, I found that particularly for the smaller chunk sizes, performance was not good at all. And when I analyzed the situation, I found that it was this update with all the OR conditions, because the optimizer got a little lusty and started adding things for Halloween protection, that kind of stuff. So I had to break this up in 3, and this leads me to update price triple, where I have 3 update statements here, one for all of these 3 cases. And this one was almost as fast as a simple loop. But then again, the simple loop is not really an issue in the situation where I must stay within my chunk size. Now, you might, as I said, this might have gone a little bit too fast for you. And if it did, you have gotten my point. I don't like these solutions. The code is very complex, only with 2 keys. Imagine if you're going to do this with 3 or 4 keys. So I like to look for alternatives. So here, this is a lot more simple-minded approach. So I'm going to define chunks in the temp table. So I got this table called chunks, order ID, product ID, and chunk number. And because that's a clustered index with the chunk number as the leading key, I'm going to fill it up, read all the key values, and I'm going to compute the chunk number by taking the row number and doing integer division with the chunk size. And then I will set up a cursor, give me all the chunk numbers in this table, and then it's going to keep on looping. So as long as I get cursors back, and then I'm going to do this update. So update B details, you multiply the unit price by 1.2, where the chunks is equal, but the chunk number is equal to chunk number, and we haven't got to match the order of the product ID. Now, that is very important how this table is built up. So the chunk, now with order ID, product ID, this means that each chunk is qualifying an adjacent set of rows in B details. And there are optimizations for this case in this server. I also made a test where I set up the chunks in such a way that each chunk was scattered all over the table. And I think that was 3 or 4 times slower than doing this one. So this is very important when you do this technique, to make sure that the chunks are adjacent. Of course, compared to the triple top loop, it's not surprised that it was slower, and in worst case up to 5.6 times slower. But I think that in that case, the join for the update did not have the best execution plan. So maybe it could have been tweaked with a hint or something like that. And I would say that the outcome of this is going to matter a whole lot of the profile of your table. So again, your mileage may vary when you test this on your own. But there's no denying we are absolutely sacrificing efficiency for simplicity. Now, this was the big temp table, and sometimes that one is okay, but keep in mind that the big temp table has as many rows as the real temp table. It's just that it's narrower, so it's smaller in size. But it still requires a full scan to fill that table, which could block writers. And of course, even, I mean, let's say it's 500 million rows, that could still be too big. So yes, this is not always a good solution, but I still think this is a viable technique because it's so simple. But the alternative is the small temp table, which you fill up one chunk at a time. This is more complex, but it's leaner. And I still like it kind of more than the extended top loop with 2 keys. So here again, I got some variables. There's a current order ID and the last product ID. They have different names because they have a different meaning than before. They will prevail towards the end. And there's also a row count variable, which I initialize equal to the chunk size. Again, I got a temp table, now with only order ID and product ID. And I'm going to set the current order ID to be the smallest order ID -1, because this is actually the upper boundary of my previous chunks, as we will see. I will keep on looping as long as my row count is equal to the chunk size, because the last chunk will typically have less rows than the chunk size. And I'll start with initiating my loop variables. Every time I write a loop, I want to initiate my loop variables in the beginning. And my loop variable in this case is the temp table. And yes, on the first round, it is already empty, but I do a truncate table here anyway. Then I'm going to fill it up again with the top query, where it says order equal to current order ID and product ID greater than last product ID. And yes, for the first order, this one is null, but it doesn't matter because this one is not going to match in the rows. And order ID is greater than current product ID on any of these. And I'm going to fill up my chunks. And I will capture the row count. So I have that for kept to the while loop. And then I'm going to do my update. And again, the way this is written, this is an adjacent set of rows again. And then eventually what I do is I found what was the upper boundaries of this chunk. So I do select top one with order ID desk and product ID descending. So I get the upper boundaries of this chunk, and then I can proceed looping. Now, in my test compared to the triplet top loop, yeah, it was at best 1.3 times slower, worst 3.4 times. And I would guess again, maybe not the best execution plan for that particular chunk size. And compared to the big temp table, it was up to 5 times faster, and some occasion, probably again due to plan mismatch, slightly slower. This here is the same script that I showed you before. And here you find the full implementations of the big and small temp tables. There is also one version with this big temp table where these keys of the chunks are scattered all over the table. And there's all sorts of variations with dynamic SQL, and there's also some performance data in that file if you're curious. Now, let's go and leave the thing about performance and talk about the impact of the application. If you're not doing chunking, everything will be one transaction, and the application will see or either everything or all. Or maybe if the transaction is going on and you're not using any kind of snapshot, it will be blocked, but you will not see anything that is half-baked. Now, if you introduce chunking, now how will application behave if it sees data? Well, it's processed halfway. And how will users react? They see, well, here is some updates, but some of the data is from yesterday, and some data is new. That could be confusing, or maybe it doesn't matter. So this is, and I would also say this is even more pronounced if your operation is interrupted, either by accident or purpose. So, for example, it could be that you know that, oh, I can only run this at night, like between 2 and 5 o'clock in the morning, something like that. So you know it's going to take days to do this operation. But it could also be that it stops. And of course, then users or application may come in and see the half-baked data. It could be the case that you can just shrug your shoulders and say, well, it doesn't matter, that's no problem here. But it could also be that you have to make substantial changes in the application to do this. And I would say this as a kind of a hint. If you have an operation that today is just monolithic and you say, I want to break this up in chunks, you probably have to think about this for quite big. What is going to happen? Maybe we have to somehow hide the half-baked data or whatever. Now, let's talk about resuming chunking. So your chunking operation is running, but it stops, either by accident or by purpose, because again, you have scheduled to only run a certain hours, because you can only run it during nighttime, for example. And we're going to look at 4 canonical operations, how to deal with this. And the first one is a purge operation. So I got here purge all data. It's sitting in purge state and it's size. And I'm going to do this in my big trans table. You may or may not recall this, but this big trans table does not have a leading index on transaction date. So I don't want to loop over this. So what I'm going to do is I'm going to make this once and compute my chunks. So I'm going to say transaction ID, but transaction ID is later the purge date. That's one scan. And I'm going to use row number, integer division by size to get the chunk numbers. But then I'm not actually going to keep those chunks numbers. I'm simply going to just take, okay, set up a cursor where I get the min and max trans ID. This is also just one more looping technique or chunking technique that you can use. And then my chunking operation is very simple. I'm going to do option recompile here, but I'm just going to delete these rows. So anyway, this procedure is running and now it stops because the server crashed or because you simply had scheduled it to stop after some time because you have added some logic saying, oh, is it past 4 o'clock? Oh, stop. Now, how do you deal with this? Well, what has been deleted has been deleted. You can just start over. That's very simple. Then we have this one, insert top plane, which this is the one we looked at before, the one we are copying data from big trans to new trans. Now, if this one crashes halfway through, how can we deal with this? Can we just restart? No. That is going to die because we will start from the beginning. So when we come here, that will be a primary key violation because we're trying to copy a row that we already have. There is a very simple way out. Here is update top restart, where rather than just saying min transaction ID, I'm going to first look at new trans, and if there are data there, okay, I will take that one, add one, and then I will continue my looping. So it was very simple in this case. Then I got update absolute. It's called absolute because what I'm doing here is I'm just saying updating a column with some specific value. Well, that some value could actually be a subquery, but the key is I don't use the value of new call. That's why it's an absolute update. And this is just this plain top loop again. I got the min or ID. I got the max or ID from this chunk size, and I'm going to do in between, and this time I'm using dynamic scale. Now, if this one crashes, if I restart, nothing will go wrong in terms of functionality. Absolutely not. However, you will redo work. You will go through and update this row that already has been updated. Well, you could add this filter saying new call is null, so it would just, okay, but then it has to search through all these rows. So a better alternative might be to say that, okay, update episode 2, I'm going to start with finding which is the first row which I haven't updated. And of course, this presumes that new call will never be set to null when you're doing operation. And then you can do the whole thing again, and this will be slightly faster. Now, then we have update price simple. This was the operation we looked at before. You might recall so this is a relative update. We are multiplying unit price by 1.2. Now, if this one crashes halfway through, what do we do now? Think about this for a second. I got some water in the meanwhile. Well, unless there is something very, very magic about these prices, there's only one thing we can do. Restore a backup because we have no idea where it stopped. And of course, we don't want to be there. We need something to do something better. So in this case, you need to have a better strategy. And here is update price resumable. So this starts with looking up, do I have this table called guest last ID? So the guest schema exists in every database. And maybe I'm overly fancy for using the guest schema. It doesn't have to be the guest schema. But the reason I put this in guest is it's kind of a temp table. But it's not the temp table that you put in temp to be. It must be in the database itself because it must survive server restarts. So this guest. So anyway, this guest last ID, it's a one column, one row table. And I initiate it with putting the smallest all ID minus 1 from big details. And when I go into the procedure, I'm going to read that last ID, add 1. And it's again that standard top loop, max ID from max all ID, top chunk size, etc. But there's one more thing here. So start a transaction, do the update, and save max ID to last ID. So if this one crashes now halfway through, I would just simply restart. Okay, where were I? Okay, I can continue from there. And then at the procedure, I actually drop this table. But of course, if you're doing this operation often, you may want to keep this table around. Now, let's go back and revisit some of the other operations. So let's say this here, update absolute. Yeah, we can do this, but let's say that for various reasons, I can only run this at like between 2 and 3 o'clock in the morning. And I have to start with doing this scan. It's a really big table. It's going to take 5 minutes to do this scan to find this min already. So now if I would use the same technique with saving max ID into a temp table, or in a table in the database, I could save that one. And maybe then, I could do more updates in those 5 minutes instead. And maybe then my operation could complete in, let's say, 8 days rather than 9 days or something like that. And what about this purge operation? Let's say again, yeah, this crashes and restart, but this loop is going to take this scan is going to take quite some time. Again, maybe it takes 5 minutes. And maybe there are so many rows of purge, I don't get complete that. So I need to restart again and again. And again, if I save these values in some table, okay, there is data in the table. I'm just going to delete those chunks. And only if I've exhausted that table, and I might want to do this scan because the purge state may now have moved on, so I'm going to purge even more data. That could be the case. So to repeat, well, one technique for resuming chunking, just ignore and start over. And you can do that with purges and also an absolute update. But in that case, you will redo work. There might be logic in your operation to find out where you were. Well, for instance, finding the last row inserted, very simple. Or you could add a help table to track where you are, but not in temp2e because you must, again, it must be there if the server crashes and restarts. Or restore a backup. And this is where you end up when nothing else is safe. And the more complex your operation are, let's say, for example, it's not a simple update. You're just calling this to a procedure that's doing some big massage on the data. You don't really know what that one is doing. So you don't really know, how can I fight? Because you didn't plan for it. You don't know, well, it might be the only safe option. And of course, you don't want to be there. So that's why you should plan ahead. That's very, 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 very important. Now, there is actually one more possibility to do this. Well, if we do the chunking inside the transaction, I mean, then if the whole thing crashes, it's going to be rolled back. But that will be an issue. But wait a minute. You might say, wait, this is completely crazy. Didn't we do chunking to avoid exploding the transaction? I mean, what's the point with this? Okay, stay calm. That is actually one more reason to do chunking that I haven't mentioned. You could have the situation where the performance of the query plan does not grow linearly. And yes, I have run into this situation. So let's say this, well, processing 1,000 rows, but I don't know, 50 milliseconds, 10,000 rows takes 2 seconds, 100,000 rows 40 seconds, and so on. Or it could be that it's linear up to some point, and then it starts building to disk, and performance just goes down the drain. And of course, the best thing might be to address the query, but it may not always be feasible. And as I said, I ran into this. I had a procedure that was going to, I think, levy, well, custody fees, whatever it was. And it read lots of rows and sent in 140,000 rows to a procedure that does a lot of things to book transactions. And inside that's the procedure that was a join between two table variables that did not do well with those 140,000 rows because optimizers thought, oh, one row. And I said, yeah, maybe I should put on option recompile here. But then I think, yeah, but this procedure is sometimes being called in a loop. What effects does that have? That results were not good. So what I did was in that outer procedure, I just sent in 10,000 rows at the time, still inside my transaction. Because if I would have removed that transaction, the impact on the application would have been huge. I can tell you, it would have been a nightmare to sort out. And we've been all sorts of tricky to get things going. Then we should not forget the risk for bugs. Because, I mean, if you're introducing chunking, it could be, well, adds more complexity. You're sitting like currently half asleep at your keyboard now, like this, you know. There could be some bugs, like you skipping some row between the chunks, or process the same row in 2 chunks, or miss the last 2 rows, etc., etc. So I would recommend test on a small data set with different chunk sizes. Yes. Like, well, last chunk for one is 1, exactly full, just a single row. And yes, I told you, gave you, this is a standard way to drive the chunks. But I know you will deviate from that pattern. And you will do that because it will make sense for your specific situation to do the chunking in a different way. So make sure that you test and you include every row. It was fairly small data size and fairly small chunk size, but you can verify that it's doing what you expect. Review your code, have someone else to review the code. And if possible, add some kind of assertions. For example, if you're copying rows from one table to another, well, check the row count. Did we actually touch all rows? Then you also need to test the performance. But this is quite a big challenge. I mean, there's so many variations, small tweaks we can do to all our chunking, but it will not be viable to do that because it's going to take too much time. I know this because I ran a lot of tests and this was just my big data database, which is 20 gigabytes, because basically you will have to restore from the backup every time you do this to have the same starting point. So you will more or less have to make a choice of gut feeling, but you need to test that gut feeling. And keep in mind, you're not looking for the very top performance. You want to stay clear of the disasters. You want to make sure, can we do this operation in this maintenance window on the weekend? That is when you find out. And also, don't only look at the execution time, you also want to monitor log space and temp2b consumption to avoid those kind of things. Something about indexing. So I would recommend, particularly if you're doing these large operations where you have the database for yourself, disable non-clustered index and also foreign keys. You do not need for the chunking operation, and rebuild or re-enable those later, because that can actually boost performance quite a bit for these large operations. And sometimes you may have to add an index to support the chunking operation, because let's say you're going to do a purge, and you're going to do that by that last updated column, which is not indexed, but that is the one you would like to work from. That can absolutely pay off, because you want to create ones and seek it many times. But if you may want to test this in some test environment before you do one. Changing the clustered index. Well, That's a trade-off because that could speed up the chunking a lot, but you will recreate the index twice to do this. Quite expensive if you have to stay in full recovery and could fill up the log. But here's an interesting thing. They added an SQL 2019 resumable index creation. This is actually chunking behind the scenes. So now let's talk about the last thing. Sometimes all or nothing is not what we want. So what do I mean by that? Well, so let's say this. You get a file with about 70,000 orders. And if one order cannot be inserted, well, you still want the other ones. So you can't just insert all these rows at once, because let's say one order could be a product we don't have, or it could be a customer we have blacklisted, or something else could go wrong. That could be an incorrect date or whatever. So, but of course we want all the other ones. So, oh God, we have to write a loop and process one order at a time. No. We can divide the orders into chunks. And if there is an error in a chunk, redivide into smaller chunks and retry. And eventually, few orders will be processed one by one, but only a few orders. And this is where we come again to the problem with that I don't have the database. Let's see here. So normally at this point I would start this, but yeah, well, we don't have the big D database. Very sorry for that. So this loop is just a plain loop. We're going to do one order at a time. And in Big DB there is a table called new orders, which has, I think, 67,000 orders. And it's going to do one loop, get order in, it's a simple cursor loop, order ID. And I'm going to copy these into big orders and big details. And there's a little bit of complication for this, because there's also a new details table. And there's also complication for this total amount column, which is not in new orders. And commit transaction. And then there is a catch block. So if something goes wrong with this order, I'm going to, well, for the sake of the demo, I'm going to raise an error. In the real life application, you probably wouldn't do that, because you probably want to log that to a table, because in how to proceed, you don't want to see that error. You want to continue with the next order. And then this one produces for every 1,000 rows some diagnostics. And you might notice here's raise error with no weight. And the reason I use no weight is because then you can see them as the whole thing progresses. And this one is level 16, so that is an error. This is level 0, so that's an informational message. And there is also a message then at the end that tells us how long time this takes. And there's also then a delete, so we can redo this one. And typically this one runs, let's say, well, about a minute, maybe a little faster, because this is not my normal laptop. And let's see then here we have the error handle loop. This one is doing the chunking. So again, that's the start time after milliseconds, and there's a chunk number, and we have some other variables. And here I got a table called chunk sizes, where I kept the chunks I'm going to work with. And I'm going to work with 2,000. That will be my first chunk size. The next, I'm going to try 100, and then 10. And I'm going to say that immediately. Those are too many chunk sizes in a real-world operation. If you would start with a chunk size of 2,000, you may have one intermediate, like maybe 10 or 50, but not 3. That's just, I think, too many. But I did this for the sake of the demo. So anyway, I'm going to create a temp table. That's a big temp table. That is, I'm going to put in all the keys, and then I'm going to get the chunk numbers, so all the order IDs, and compute a chunk number by doing row number and integer division of 4. And I'm going to take the chunk size is now the select max size from chunk sizes. And now I can't do a cursor because the chunks will be dynamic. I'm going to loop over this table called temp orders, as long as there is data. And entire body for this while block is a try catch block. Notice this. So I will get the next chunk, the smallest chunk number from temp orders, and I will try to import this chunk. Start a transaction, insert into big orders for all the orders in this chunk, and big details. The same thing, all the orders in this chunk. Commit this. Here are some diagnostics. So I'm going to compute the total row count, and if I exceeded the row count, I'm going to print out thousands. You're going to see that from how far this one is progressing. And again, this is level 0 race error, but with no weight. But if I would use print, you will not see the data at the end when the whole thing is completed, because then it gets buffered. That's why I'm using race error with no weight. And then I'm deleting this one from temp orders, this chunk. And here I fall down to the cache block and have the error. I'm going to roll back in a transaction. And I got some more variables. I'm going to see what is the chunk size of this particular chunk. Okay. And if this chunk size is bigger than 1, I'm going to find the next chunk size. And it says max size from chunk size, where size less than chunk size 1. You might recall I did not put 1 in chunk size because 1 is the chunk size. I always will have to try it in. So I did not put that in the table, but rather I do in isNode. If I don't get a hit here, I will be down to 1. Produce a diagnostic message that I'm redividing. And then I'm going to compute my new chunk numbers. So I got this CT here saying select chunk now and tip chunk, which is a row number, again, order by order ID, integer division by that new chunk size for this particular chunk. Now, you might think here I'm going to have to loop, join temp orders to chunk CT. I don't have to do that. I can update this CT directly. Yes, you can do that. I know the first time I saw this, it looked scary to me, but yes, this is very efficient. So I'm going to say this temp chunk and add the max chunk number from temp orders. So then I get my new chunk number. Now the else here, this is the case where chunk size is 1. So there is something wrong with this order. And I would get the error message, why it was wrong, what the issue was, and get the order ID and print out the message. And again, if it was a real world application, I would log this to a table. I would not raise an error because then an outer procedure could catch that error, and it would be bad because then that would interrupt operation. And of course, but this is for the sake of the demo. And again, I have to delete this chunk. And then that's the end of the catch block and the end of the while loop. And then there's the final stuff here, and then dropping the temp table only so I can rerun the whole thing and deleting the tables. And typically when I run this on demos, it's like 3 or 4 times faster than the other loop. But as I said, I can't run this now. Very sorry for that. But you can download if you want to play with this and try this. I should say that there are 4 orders in total that produces some sort of error when loading this. So now one challenge with doing this technique is that you have to pick the initial chunk size, and that is a bit of a guessing game. Because if you set it too high, like, well, 1 million, but then every chunk could error out and will roll back, and that will not be efficient. So here is my rule of thumb, which is absolutely just not built on any science or testing, just out of thin air. So if you expect 1 row out of n to error out, well, set the initial chunk size to like n divided by 10. And of course, assuming no other limitations, like having been nice to others and so on. And of course, again, determining that n may require some good gut feeling. Well, how often do you expect them? But then again, if you have a process that is already doing this with a loop and you want to improve it, then you might have data from that loop. How often do we get errors? And also one thing to consider is, are the errors coming in burst or are they completely random? Because if they come in burst, then basically, well, 1 block of 10 errors is basically the same thing as 1 error because it will all be in the same chunk. But if they're completely random, then you will have to have a smaller chunk size. And I would say if you're the division will be like 100 or 1,000 at a time, not smaller. I remember we did this many years ago. I wrote the spec and the colleague implemented this, and he went for a chunk size of 1,000 and said, oh, if there's an error, I'm simply going to take 1 by 1. And I think that worked out fairly well. So we are going towards the end, and I'd like to do a summary of what I've been talking about. So yes, chunking is nothing you use every day. It's a trick you have in your toolbox for these really large operations to keep the transaction log and temp to be in check, and to avoid conflicts with the rest of the system. And if you're doing these really large operations, make sure that you have transaction log backups running, and you may have to reschedule them to run more often. Indexing is critical. Your chunking must always follow an index, preferably the clustered index. Repeating scans is very, very costly. And the top method that I showed you is a very generic way to drive the chunks. Work with any data type you can put an index on, and it works even with non-unique indexes to some extent. And for multi-column keys, only work with that second level if you really have to, if you have to be constrained to small chunk size. And if you have to do it, well, defining chunks in a turntable is less efficient than extending the top loop, but it's oh so much simpler and less error prone. And make interval variables known to the optimizer with optional recompile sniffable through dynamic SQL. And dynamic SQL may benefit from full scan statistics. And don't forget to consider how the applications may be affected. Design your loops so to be able to restart when they're interrupted. Make sure that you plan ahead. If needed, create a help table to track where you were so that you can resume easily. And don't forget to test for correctness, for performance. So this is the last chunk. My name is Erland Sommarskog. My email address, again, is sql@sommarskog.se. You're more than welcome to drop me a line if you have any questions related to this session or anything else about SQL. You find slides and scripts on my website, sommarskog.se/present. And here's also the download link to BigDB. And so, for example, you can do the error handling demo that I was not able to do because I had some issues here. And this is the download is 3 gigabytes, but it's compressed back up and will be 20 gigabyte. And it's for SQL 2016. Oh, that's one thing I'd like to mention, particularly if you get in communication with me, because I basically only scratched the surface of this complex topic. I mean, as I said, this is nothing we do every day. So every time we do this, we find, oh, wait a minute, here's something. I didn't think about this. So if you have some tips you want to share with me, you're more than welcome. Okay, thank you very much for listening. I haven't